Hello all, welcome to this new module of the course on electric vehicle dynamics and motor drives. And in this module we are going to discuss some aspects of the magnetism and the control of the SRM, BLDC and induction motor. We'll also have some discussions on the control of the PM SM motor, and we will see how these basic concepts are going to be useful in our practical applications for the electric vehicle. So let us start with something which is more critical for the machine when we talk about. It is the basics of electromagnetism and BH curve. So essentially what we are talking about when we go on to understand how the switch reluctance motor or BLDC or PM or induction machine are required to be operated, we need to understand some fundamentals about the electromagnetic theory. And this is where we come to some fundamental principles and rules which can suggest us that what is the way in which we should approach a particular system. So, machine being a complex system, we will start our discussion with a simple electromagnet or a simple magnetic core. So the problem given over here is quite simple, is that we have a core provided over here which is having a permeability of mu, and it is having a cross-sectional area AC. The length of the core, mean length of the core is basically LC. We are providing some n number of turns, a coil which is having n number of turns which is around this core, and I current is flowing into that winding. Now what we are required to compute is that what is the amount of flux flowing in the magnetic core. So there are several ways to understand that, how to compute this. There are many theories, many terminologies which are evolved, but we need to understand that how these theories are evolved and how these are correlated to the property of the material and other phenomena. So here we will take help of Maxwell equations. And we will see how we can use these Maxwell equations under this particular scenario to solve our geometry. Now, fundamentally, there are four equations which are basically correlating the electric field density, electric field intensity, magnetic flux density, and magnetic flux intensity. These four quantities are basically correlated through set of equations, and that is what we know as Maxwell theory. Now, I will take the particular form of the integral form of these equations to understand how these can be applicable for the system what we are having. So when we talk about the integral form, we have basically integrations happening over closed surface or integration happening over a closed contour, a closed path. So we will represent the closed surface with integral having a subscript of S and closed path integral having a subscript of C. So the first equation, which is basically the surface integral, closed surface integral of electric flux density, this basically suggests that it is equal to the charge enclosed within the total system, within the total boundary. Now, if we have the closed contour integral of electric field intensity, we are going to have term correlating the magnetic flux density for the same surface. Now, if we talk about the closed surface integral of magnetic flux density, this is supposed to have the total magnetic pole enclosed within the closed surface, and because there are no monopoles existing in nature, which is why the surface integral of magnetic flux density over a closed surface is basically 0. Now we have the closed contour integral of magnetic field intensity, and this is basically having two terms. One which is suggesting that the total current enclosed within that path, and also a term which is correlating something called as displacement current, which is very much visible in case of capacitors and when we are going for sufficiently high frequency. Now, for our application, when we are trying to solve a magnetic circuit which is of this nature, we need not solve all the four Maxwell equations. We can have certain assumptions which can simplify our problem. So, couple of assumptions what I would like to state over here. First, the magnetic field lines are mostly confined within the geometry. So, the meaning is that when we are talking about the core, the field lines are more or less confined within this core itself, which means that field lines going out of this core and out of this magnetic circuit are negligible or in a very small quantity. The second assumption what I will have over here is that the cross-sectional area, which is represented as AC over here, is uniform. Now, with these two assumptions, I can basically take a closed path, a closed contour within this core. Say, for example, this dotted line is shown over here, and I can have a surface which is correlating to this contour. And I can apply the third and fourth equations which are shown over here. So, considering the fourth equation, what we have stated that because the frequency is not very high and the capacitance is also not significant, we are going to have nearly zero displacement current in this system. So we are essentially having I enclosed, which is basically going to appear in this expression. Now, because our path is very much aligned along the magnetic field lines, the field lines are also aligned along this path. So H dot dl is going to be a simple product of H and the differential length. So this can be simplified to H times of the mean length, which is given as LC for the core, is equal to I enclosed. Now, this quantity I enclosed is representing the total amount of current which is enclosed within this closed path, which means that if I amount of current is flowing in one turn and there are n turns totally given over here, then the I enclosed is basically equal to n times of I. So we can rewrite this expression as this. Now there is one more equation which is basically correlating the magnetic field intensity and magnetic flux density through the property of the material, which is basically the fundamental equation B equals mu H. And because we are talking about quite uniform magnetic materials, we can take the scalar form of this equation. Here the permeability mu is basically product of relative permeability and permeability of air. The value of mu 0, we are aware that it's 4 pi times of 10 raised to the power minus 7, and mu r for a given ferromagnetic material, for the commonly available ferromagnetic material, can vary anywhere from 1000 to 4000. So we are talking about a normal magnetic material, which means we are not getting into any kind of special design for the core. So what essentially we have over here is that the simplification of that equation, which is having h times of Lc, which can be written as b times of Lc by mu is equal to Ni. Now, we all know that the flux and flux density are related as this, the area of cross section of the core times of the flux density. Once again, due to geometry, our field lines are very much aligned along the axis of the surface. So which is why the dot product becomes simple product of the flux density and cross sectional area. So now we have the expression for flux that can be represented in terms of different terms which are relating the geometry and excitation. The term Ni is also sometimes represented as the magnetomotive force, MMF, which is analogous to electromotive force in case of electrical systems. So if we write it in this manner, what essentially we are trying to say is that MMF is equal to flux times a quantity which is representative of how much resistance that path is offering to the flux. So in magnetic circuit, this term is called as reluctance. And then the equation becomes quite analogous to what we have as Ohm's law. So which means that the total circuit which is there, we can represent as if there is an electrical source, there is a resistance, and there is current flowing into the circuit. Now this is one representation, and in this manner we can easily compute based on the geometry what is the reluctance of the total path, what is the total magnetomotive force over there, and then what is the flux confined within the system. Now once we have this information, the next step would be that what if the path of the flux is non-uniform, if there is some non-uniformity in the path of the flux, which means that there could be a small slot cut open in the core which can be shown like this. So here what we have is that there is a small section which is cut out from this magnetic core, and now we have a small air gap having a length g which is coming within the path of this magnetic circuit. Now again, when we are going by the analogy, we can say that it is a kind of another additional reluctance which is coming into the path. So if we have the magnetomotive force given by the representation, we have one reluctance which is offered by the core, the iron core, and another reluctance which is offered by the air gap. Now, since these dimensions are pretty well known, and we are sure that the section which is cut out is having cross-sectional area which is very same as the cross-sectional area of the core. So which is why computation of Rg can be done in a simplified manner. Now the flux what we are trying to compute over here can be represented as where Ag is quite similar to Ac, so this can actually be written as Ac. So if we take out these terms which are common, we can find that so here what I have done basically is that the permeability of the material can be broken into two parts. It is written in terms of relative permeability times of the permeability of air. So this is the number what I had earlier suggested, going from 1000 to 4000. So now once we have this, if we compare these two terms, what we find that essentially the reluctance of this air gap is going to be the dominant factor in deciding the flux in the whole system. So this can actually be approximated, and many a times flux can be simplified in this manner: the total MMF divided by the reluctance offered by the air gap. So these are some of the ways in which we can solve the flux in the magnetic circuit. Now once we go for the machine analysis, we also need to represent these quantities electrically. For having the equivalent circuit for the machine, for having the operation of the machine through power converters, we need to understand that how do we represent these quantities electrically. So for example, the core what we have taken is essentially a coil, and it is having a voltage applied across this, say an AC voltage V. In response to that, there is flux flowing in the coil. So if we ignore the resistance of the coil, what we are trying to have is basically the EMF induced by this flux across the coil should basically obey the KVL. So we should have some of all the EMFs within this loop going to 0. Now when we try to compute this voltage which is going to appear over here, this can be computed by the negative of rate of change of total flux linkage. So there is a new term which is called as flux linkage. So what is the difference between flux and flux linkage is that when we have phi flux flowing into the core, each and every turn of this coil is basically linking the same core. So the total flux linkage for the coil becomes n times of phi. That is the difference between flux linkage and the flux flowing into the core. So which is why lambda can now be represented as n times of phi. And from the Faraday's law, which we have stated over here, this can be written like, so in other words, what we are having is that V going equal to d lambda by dt. Now we need to understand, because these are again magnetic quantities, lambda is flux linkage, phi is flux, so we need to have some electrical representation of these quantities. Now if you try to expand phi within this expression, what we are having is that Ni by R here we can see that there are again two parts which are appearing within this expression. One based on the excitation what we are providing, and another is totally dependent on the geometry of the core and the coil what we have kept on the core. So this is the term which is represented as the inductance of the system, of the electrical network what is appearing over there. So which is why lambda is many a times represented like this, and the inductance of the coil or of the system can be given by this expression. So what we are finding is that when we are trying to apply KVL for this system, both the quantities L as well as I are within this derivative. Now, in a most general manner, we have the possibility of having a constant inductance while our current is changing, or we may have current as a constant quantity and inductance as a varying number. So in general, any system may have both the terms appearing within this KVL. Now, when we classify the systems in different manner, we consider the systems in we classify the systems in a manner that we can call as linear and non-linear. So the first term, where our inductance is constant, we often refer to such systems as linear systems, where our inductance is constant, however current is varying. And whenever we have inductance varying because of any change in the shape of the system or any other plunger moving into the system, we have L varying, and that is why we call them as nonlinear systems. Now, how this is going to appear and what is going to change, that we can analyze in some time. So this expression is going to be useful for further analysis. However, at this point, let us take a quick look at another important phenomena, which is relating the property of the material. So when we are talking about the excitation, say we are providing excitation I and we are getting the flux linkage of lambda, it is essentially the same expression what we have written as B equals mu H. So one equation is basically true at microscopic level, and another expression, this lambda equals Li, is basically relating to a particular geometry, but essentially it is the same phenomena what is occurring over there. We may expand the terms of lambda and Li, and we will end up having this expression B equal to mu H. So let us quickly do that exercise. This we have called as our magnetic field intensity. So we end up coming to the same form of the expression. So the meaning is that when we are talking about a particular geometry, about a particular system, we can basically represent the excitation which is in form of I, or it could also be written in form of H, and the result what is appearing in the system in form of lambda or in form of B. Now when we talk about any particular magnetic material, mu is going to play the important role in deciding with respect to what excitation we are going to achieve what value. So let us take example of air where we have mu zero value coming as a very small number, 4 pi 10 to the power minus 7. So basically what happens, what it suggests that if we are trying to have a coil which is air core coil, and you provide some excitation, the flux density or the flux linkage are going to rise in a very mild manner. So we need a large excitation to be able to achieve a significant value or appreciable value of B. However, on the other hand, if you talk about a particular magnetic material having sufficiently large value of mu r, what is going to happen is that the slope of this line is going to increase by a significant amount, and it is going to see a rise in B which is much more steeper compared to air. However, every material has certain limitation on flux density. There is a limit up to what value the flux density can rise. So which is why beyond a certain limit the slope of the line starts changing, and then the slope becomes very similar to what we have in case of air. So what is essentially happening in this case is that the mu r value, which is basically constant over here, has now started reducing, and by the time this saturates, mu r has become nearly equal to 1. So if you compare the rise in flux density for a given change in excitation, it's going to be much larger in the initial portion of the graph compared to the portion of the graph which is closer to saturation. This is on account of changing value of mu r. Now another property which this is popularly known as the BH graph, which this BH graph exhibits, is that if you have not taken the core towards saturation and you try to reduce the excitation towards zero, the path of this flux is not same as what was taken earlier. So basically it does not come back to zero value, rather it comes back to a value which is non-zero on the y-axis, and this Br is called as remanent magnetic field. Now sometimes this Br value is essential, sometimes we want a small value of Br. So whenever we are talking about materials where we are requiring properties like a magnet, or we want to have some residual magnetism, for example in case of DC motors we do need to have good value of VR available over here. Now, based on the material property again, if you start exciting the system in opposite direction, there may be a point, there may be excitation on the negative side of the y-axis, where on the negative side of the x-axis, where the value of B would come back to 0, and this Hc is called as coercive force or coercive field intensity, which means that forcefully we are bringing it to 0 value. And then as we proceed on the other side, we keep giving the excitation on the other side, again it goes towards the saturation, and once we come back, it's again going to take a path which is different from the previous one and going to have a remnant magnetic field on the negative side of the y-axis, and then this process will basically follow, and there will be a loop which is known as the BH loop for any given magnetic circuit. Now, based on the values of BR, HC, one classification for magnetic material we have seen in the previous module, that is called soft and hard magnetic materials. So essentially, soft magnetic material means the value of Hc is small, so it can quickly die down. The remnant magnetic field can quickly die down, it can quickly be magnetized, and it can quickly be demagnetized. Something like this. So maybe for clarity I'll draw it again. So the value of Hc is basically suggesting that whether the material is to be considered as hard or soft material. Some of the machines, as we suggested, that DC motor may require hard material, whereas for AC machines we are okay with the soft magnetic materials. Now, this remnant magnetic field, the remnant field flux density, and this Hc play a very important role in deciding the quality of magnet. When we talk about permanent magnet, so essentially permanent magnet is basically going to have the BH curve which is lying in the second quadrant only. So for example, it is already magnetized, which means that there is a remnant magnetic field, and if we try to load the magnet, by loading what I mean is that the magnet generally is required to be kept in a closed magnetic circuit, closed magnetic path. So if we are taking out of this, which means the magnet is kept, say, in air or in some other magnetic path where the reluctance is more, it is going to lose some magnetic flux density, some strength it is going to lose. Now, typically, there is a BH curve path which is indicated for the magnet by the manufacturer. Now, when we are doing this, taking the magnetic out of its closed path magnetic circuit, we are going to see that there will be some reduction in the remnant magnetic field. And if you try to keep it back again into that closed path, we will find that, and it's another observation for the magnets, that it never goes back to the same value of Br, but rather it will take a different path and it will have a little lower value of this remnant magnetic field. And every time we repeat this process, now it is going to take a small contour about that new axis, which is basically called as recoil axis for the magnet. So this is property exhibited by magnet, which can be correlated to, say for example, you have a spring which is having mass m. In unstretched condition, the displacement from this point is basically zero. But if you hang it little bit, leave it little bit unsupported, you leave it unsupported, this is basically going to lose some length over here. Some x is not, no, some non-zero x is going to be there for the length of the spring. So which means that we are losing some potential for the spring, and same thing is happening with the magnet. So what is expected from a good magnet is that we should have a high value of Br, we should have high value of Hc, and also because this recoil axis phenomena is going to happen, the BH curve of the magnet should be very, very close to the recoil axis for long-term performance of the magnet. So some of the examples we can see over here, some of the practical magnets what we have, and it's taken from the book by Fitzgerald. So what we are having is that different type of magnets are provided over here, and the BH curve is also given. So for example, if we take the example of Alnico 5, which is this graph, it's having pretty high value of remnant magnetic field. However, the problem is that the Hc corresponding to this particular magnet is very, very small, which means that this magnet can be demagnetized very, very easily. So definitely not a very good choice for having a permanent magnet machine or any other thing. The second option could be Alnico 8, which is some superiority it is showing in terms of Hc, but there is a reduction in value of remnant magnetic field Br2. However, the advantage what we are gaining is that the coercive field is basically slightly higher compared to Alnico 5. So there is some advantage that yes, the magnet is better in terms of performance, in terms of longevity, but however, the value of Br, the strength of the magnet is basically coming down. Now another type of material, if we see ceramic 7, which is showing much higher value of Hc, however, the strength has come down significantly compared to Alnico 5. So we are kind of having some kind of compromise on the strength of the magnet to gain some kind of higher coercivity. Whereas if we talk about the rare earth metal magnets, so samarium cobalt, which is shown by this graph, it's having good value of Br, which is basically better than Alnico 8, and very high value of Hc. So from the invent of these rare earth magnets, we have found that suddenly we are having so many machines and so many other systems which are being fabricated having these kind of magnets. And the most superior one out of all these combinations, we are having the neodymium iron boron magnet. Here the remnant magnetic field is as close as Alnico 5, and the coercive field is significantly higher compared to any other combination what we have seen over here. So which means that if we are targeting to make a motor for electric vehicle, this could be a potential contender for having a good quality motor for that. So this is some general discussion about the magnets. Now these fundamental concepts, when we are trying to apply these fundamental concepts into a practical system, we need to understand that where we are going to have the linear system and where we are going to have the non-linear system. So the meaning is that how we are designing our system, So based on that, we need to consider whether the first part of this expression or the second part of this expression. So I'll take one example to illustrate that. Say if we have an electromagnet, a C core electromagnet, to keep it simple. There is a coil having n number of turns, there is current I flowing through that, and we have a plunger which can basically move, but it is hinged at one point, so it can rotate about this point. And at this point we have air gap G coming between the other part of the electromagnet and the plunger. So our general understanding is that whenever we try to apply some excitation to this coil, there will be field lines which will be linking to the plunger, and the plunger will have tendency to move towards this electromagnet. That is what the general understanding we have. Now, what is happening in these cases, based on whatever concepts we have understood so far, is that whenever we are having variation in the air gap, the reluctance of the system is going to vary. And we understand that predominantly in this system, the reluctance offered by the air gap is going to be the dominant factor. So if reluctance is varying, this means that our inductance, which is associated with the system, is also going to vary. Now, if we talk about two positions, one where the plunger is at gap G, we are having maximum value of reluctance. And so, because inductance or reluctance is inversely proportional to reluctance, or this inductance is inversely proportional to reluctance, we are going to have minimum value of inductance in this case. Second position, if we take where the plunger is, say, completely aligned, it is quite close, it has rotated and reached to a position where G is nearly zero, the air gap is nearly zero, we are going to have minimum value of reluctance in this case, and which implies that we are going to have maximum value of inductance for the system. Now, when we are trying to have operation of this kind of plunger, and say we are operating with a constant current I, once again let us try to have the excitation and the flux linkage on x and y axis respectively. So we have the excitation I on the x-axis and the flux linkage on the y-axis. What we are saying is that we are moving from position 1 where we have L at a minimum value, and we are going up to position 2 where we have L at the maximum value. So if I draw these two slopes, say corresponding to L min and corresponding to L max, the L min position can be represented in this manner, the slope can be represented in this manner, and L max can be represented in this manner. Of course, there is going to be some saturation limit for lambda and all, so that is considered. However, at this point we will not get into saturation, and we will discuss only the normal movement of the plunger, how it is happening and what is happening with the total system. Now let's say you provide a constant excitation for I, which means that while holding the plunger in position 1, we have increased the current up to certain rated value, say up to this point we have increased the current I, and then we allow the plunger to move towards the electromagnet. So how the path of lambda is going to be within this graph? So of course, when we are starting the excitation, lambda is starting from 0, and initially it will follow the L min path, and it will keep on increasing as I is increasing. Now, say it has reached to a point A. After that, we are allowing the plunger to move from one position to another position. So what will essentially happen is that basically we are moving vertically from this point A to a point B on this second line corresponding to L max. So once the plunger is moved, we do have the facility to reduce the current and bring the current down to zero. Now in this whole process, the work done that is happening in the system is basically, or it can be correlated to the energy stored in the system. So what is essentially happening is that whenever we are talking about the excitation and the flux linkage, there is always some energy associated with that, and that can be represented as half Li square, which is commonly known to all of us, can also be written as half lambda I. Now, when we are talking about constant current system, where we are allowing the plunger to move from one position to another position, the change in energy is basically going to be so essentially on this graph what we are suggesting is that, say this upper triangle OAC, this is the co-energy associated with the system when we are talking about, when we are keeping the plunger in position 1 and we are keeping the excitation at this point. And we have this triangle OBD, the shaded area, which is basically the co-energy associated with the electromagnet when we are keeping the excitation I and we are keeping the plunger in this position, position 2, where the L is max. So what is happening essentially is that if we are taking the full path, which means the plunger staying at position 1, going up to the full excitation, then plunger moving to point 2, where the point for lambda has changed from A to B, and then we are bringing the excitation back to 0. In this process, we are confining some energy within this small triangle, OAB we can say. So this energy confined within this OAB can be approximately said as the work done by the system. Or in other words, what we are stating over here, we can consider this as well. So now, if we have to compute the total torque applied on the plunger, it can be taken as the derivative of the co-energy, the rate of change of co-energy in the system. And this can essentially be taken as where theta is the position of the plunger. So a very simple phenomena, that we have provided the excitation and plunger has moved from position 1 to position 2, and in this process we have done some work, and that is what we are trying to compute. And then also we have computed the torque applied on this plunger from whenever we are providing the excitation. Now this has direct correlation with the motors which are basically operating on the principle of reluctance. So the switch reluctance machine is basically one of the example of operating the or achieving the rotary motion on basis of the change in reluctance. So we'll see in the next lecture how these concepts can be applied and what to expect from a basic switch reluctance motor and how to control that, and how to design the power converters for the same machine. Thank you.